Hey, how's it going, guys? In this video, I'm going to walk through this problem from Algo Expert. This is called Boogle board. So we are given a two-dimension array. We also can call it a matrix or potentially unequal height and width of the matrix containing letters. So as you can see, there's an example over here. That's the board, right? And this matrix represents a Boogle board, and we are also given a list of words over here. That's an example uh, of a list of words. Okay, and we need to write a function that returns an array of all the words containing in the Boogle board, and the final word do not need to be in any particular order. So a word is constructed in the Boogle board by connecting adjacent. So by adjacent we mean horizontally. So this is horizontally or vertically or diagonally, right? So we have positive diagonal or negative diagonal letters without using any single letter at a given position more than once. So we cannot go back and forth, right? That's what it means. So if the word is like TH or THHT, right? So we cannot be like TH and go back HT, things like that, right? So we cannot use it more than once. And while a word can be, of course, have repeated letters, this repeated must be come from different position in the board, right? That's what we just said. In order for the word to be contained in the board. So, and also we need to know that two or more words can be have overlapped and so share the same word, same letters in the Boogle board, right? So basically, for example, this or on a vertically, so we can share the same letter of I, things like that, right? So we can share the two words or three words can share some letters in common. Yeah, this is an example that we talk a little bit about. So let's look deeper into it. So this right here, THIS right here. Let me zoom in a little bit more. And is right here, and Boogle right here, Boggle. So again, we can go diagonally. Um, yeah, this is some of the word I can see. Oh, uh, non non-repeated, non yeah, NOTRE dash repeated. So we go here and then go down and then go here, go left. Okay, so um, this is an example of how can we look around all these adjacent words. Okay, and feel free to pause this video and think about how we can solve this problem. And this is not an easy one, but I think it's a very good problem because it uses a couple of different data structure and algorithms. And here I'm going to talk a little bit about my approach. And first thing is that we can use a trie or a tree that we can build a tree that we can just scan through the entire board at once. So at the same time, when we scan through the board at once, and then we will also at the same time we search for different words. So a trie is very helpful for a case like this, right? And then along with the trie, and we will need to use a backtracking, also a depth first search, a DFS to traverse um, the board. Okay, and yeah, again, so at this point, feel free to pause the video again if you can. If you couldn't solve it um, at the first glance, and feel free to pause in here and think about how we can implement what I just said. Um, and then I will show you the solution. Okay, I'm gonna show you the solution right now. Oops, I'm gonna show you my solution right here. Let me zoom in a little bit. Yeah, so here. So first thing first, we need to have a trie. So you have a class named trie. Initialize it. So we have two properties with the class. One's the root, which is empty dictionary, a root node, and also an endpoint. So essentially, when we detect there's a asterisk in the keys, and in one of the key, and we mean that we know that this is going to be a terminal point. So I call it and then we have an endpoint right here. That's the asterisk, and also we have a method. I call it add, so we can add words to this trie, and we will use a nested dictionary to build our trie, right? So for example, the current node is the first current node will be at the root node for each of the character in the word that we are adding to it. If the character is already in the current node dictionary, if not in the current node dictionary, we will just create a new dictionary. And if it is already in the dictionary, so we don't do this step, and then it will move to the next level by this, right? Current node equals to the current node, the previous current node, or as called previous node, and the current character, right? So basically, this is how we move one level down in the tree. Okay. And also, I just pulled up a Wikipedia page on trie this data structure, and so that you can visualize it. So this is how we can build a trie tree, and this is how we can just and we used a nested dictionary to build this one, to build a trie, and this is how we can move to the next level. And this is the terminal word. As you can see, if we have the T, the word, right? So we go from the root node and the T node and then TE, which is here is actually a E, right? But the E comes from the T, and then there's an A at the end, right? And then this is the terminal node that we have the word T here, or TED over here, where we have another node that came out from the E node. So we have the TED over here, right? And yeah, so if you want more visualization, yeah, feel free to browse this Wikipedia. Okay, back to our code implementation, and yeah, so this is a simple implementation using a nested dictionary to build a trie. And now we can look at how we can solve the problem. And first, we have to build a trie first, right? And for each of the words in the given list of words, so we then add each of the words to this trie, so we can build our trie tree. So immediately you can see that this is the first step, right? So the term complexity is going to be a big O of a number of letters, number of characters in the list of the words, right? Because basically you have to first traverse all the words, and within all the words we have to go through each one of the characters, right? So you can see the term complexity is going to be big O of number of characters, and that will be also a space complexity, because we need the tree to be that big to contain all the letters. And yeah, so and we will talk a little bit about this helper function later. Get neighbors, and also yeah, this one I will go through this later. And yeah, I want to go through this for loop with you first. So first, we need to have a number of rows and number of columns. So this is some helper variables. So number of rows is the length of the bird. The length of the board. And number of columns is just take the first row and look at the number of columns over here. So n rows and n columns. And so this is how we can traverse each one of the spots in the matrix, right? So by matrix, I mean the board. For each of the row and also for each of the column. what you're gonna do, we're gonna export, right? We're gonna export that row and that column of the, I mean, by this R and C is the index of the board, right? So, and also we will provide a root node to as a starting point to this export function. So now let's look at the export function together. So we have two sets in here. One is the scene set that keep track of what kind of index that we are looking at, that we are exploring, essentially exploring, and also we have the result set which we will return at the end. So the result is gonna be is using here. So we return the all the word that we found from the list of the given word, right, over here, right? It's gonna be a subset of all the given word. And so this function export. So if the R index and the C index is already in the scene set, that means they are being exported already from other path. So we return. So we don't need to do anything more. So we just return it. And then we look at the current character in the board. So we are given the R index and the C index of the board, right? So and we look up the character that we're looking at. If that character is not in the given previous node, so that means that the trie tree in the current node or on the previous node does not contain such a character. So there's no need that we need to move forward, right? Because it's simply is not in the character. It's not does not satisfy this requirement of the list of the words, right? If that's the case, you should again. So we will return as well. So if we can bypass these two if statements, that means it's not being explored, and also it is in one of the previous in the previous node's key, right? So it can move to the next level. So the current node is gonna be the previous node that take the current character, and this is gonna be the next level dictionary. And now we can further export this coordinate. So we will put it to the scene set, right? Scene dot add this coordinate, and also if the final word, if the final character, right? If the final character is exactly, if that character is in is actually is if it is endpoint in the current node, means that we have already found a word, right? So and that we can just add it to the result, right? Because remember, trie.endpoint essentially over here, that's the asterisk, right? And but that is actually a word, right, over here. So current at the current node, which is the final node, that at the asterisk will be a word, right? With the word that we're adding. So we will use that. This is where we use it, right? The found word is actually in the current node of the asterisk, right? And then we just add it to the result. Okay, and now we will export the neighbors. And I will talk a little bit about these util functions, how to get the neighbors. It's pretty easy. I'm gonna show it to you later, but I just want to understand the idea first. So for all the neighbor in the neighbors, right? So what kind of neighbor it is? The neighbors are surrounding the coordinate that we are exploring, right? The coordinate that we are exploring for all these neighbors. We just further export, right? So we add it to the next level, right? The neighbors coordinate are the row index and column index. Also, we also provide the current node for the next level, right? So the current node is going to be the next previous node right here. So it's going to be this function will be called recursively, okay? And And finally, we will remove the current index, right? After we export all the neighbors, because we added to here, and now we are done. So we will remove it. So the reason why is that, so for example, the first path that we're exploring will be, let's say THI, and then go down M. But we found that this path is not going to work, right? THIM. So everything in here will be marked as seen. Okay, but we realized that this path is not going to work out, right? So we backtrack. So the way, but it could be the case that we want to revisit the I, but from a different path, right? So for example, it could be for THI and then I here, right? THII here, right? In that case, we have to remove this one as seen, right, from the pi path, right? THIM, because we want to visit this node from the other path, THII, right? So we have to remove the one that we explored previously, which didn't work out, but we go to the same node from the previous path. And the way that we can do that is just remove it, right? So we are exploring a particular path by adding the scene set, and after we exploring all the neighbors, we realize this path is not going to work out, so we will remove it, right? And that's it. And this is the core DFS function. And now we can talk a little bit about this get neighbors function. It's pretty simple, but it's pretty tedious. So for all the neighbors, if the neighboring coordinate does not fall out from the border, so we just add to the neighbors list. At the end, we just return this list, and that's it. So let's submit that. Yeah, all tests passed. Yeah, this is my solution to this problem. I hope you find this helpful. Thanks for watching. See you next.